what else? Jackie, did you try if he can share slides? Does he have a?
Yeah, do you want to try quick? Just make sure your PowerPoint can be shared.
Yeah, sure.
And then John, maybe we'll wait till like 4:02 or so, and then you can do the intro.
Okay, are you gonna give some initial instructions at first, Jackie, in terms of questions, no. Right? Or no? Do you want me to say that? What do you typically do?
Sure, I'll do a little bit right at the beginning.
Just the basic, instructions of typing questions on the chat box, and I think we have 2 graduate students, right, Neil and Dane, that will be monitoring the chat, correct?
Yep.
Okay, perfect.
Yeah, I'll do that. Well, a little after 4, I'll do that, and then we'll go. Great, Lauro, that looks great.
Yeah, we have it. We can
Jackie,
see it.
Jackie, I think what happened one time is when the person speaking disabled other folks to be able to, the student to be able to chat.
Okay.
So I think when Dr. Vianna's done speaking, if he stops sharing, then that should open it back up for you guys to, he's shaking his head, yes, for you guys to have control so that the student can participate.
Perfect.
Yeah, that was just a little mistake on the speaker's part.
Well, that's great.
Jackie, you were asking me something?
I don't know.
About some data, about data stuff?
Oh, I just said you've been doing amazing.
Oh.
I said, like you said, I think like every week I see another another group paper coming out from you guys. It's amazing.
No, I try to be just 10% of Jaume Padilla behavior. I had a really good colleague as a postdoctoral fellow, but I can try, but I will never be, I don't know, 10%.
Right. You're right.
And his team is not doing that great, Barcelona. I'm sorry, Jaume.
We're not.
Well, somebody emailed me last night at 1 and they got a response back from me at 3 a.m. So, we're trying to keep up as much as we can. I suppose I could have set my email so that that response wasn't returned until 7 in the morning. And that would have made the student feel better.
So, Jaume, you are doing data collection on a regular basis, no problem.
Every day.
Okay.
We are full force both on the animal side of things and on the human side of things, simultaneously. So,
Okay.
no real restrictions there other than just taking a lot of precautions. And that's, in terms of occupancy in the building here, I'm at the Dalton Cardiovascular Research Center now. I moved to the Dalton. I don't think I told you that.
No.
But that's where we do all the basic work now. And we have some, we have some guidelines or instructions in terms of occupancies to not, we're not at 100% occupancy yet.
Okay.
But we are able to schedule things around and make sure that we can stay productive.
Okay.
Yeah.
Perfect. Yeah, I've been not that optimistic, right? Optimistic. I've been really pessimistic. So I hope that before March, I'll be fully, back.
Oh, that's crazy. 1 year of shutdown. I mean, I didn't realize that was so bad.
Yeah.
No, sometimes I talk to Alan. Alan keeps emailing me. So I knew that human studies were not allowed yet in Brazil, but I didn't realize that it was going to take that longer.
That's my impression, right? But I hope I'm wrong. Maybe December we are back, or November.
Yeah.
I'm not sure. So it depends on how the curve is going down.
That's right.
Yeah.
All right, I think we'll get started.
Okay.
First, I'm just going to thank everybody for coming to the Mizzou NEP weekly seminar. As everyone knows, this week's entirely virtual. So we are really lucky to have Dr. Vianna. And for those that you came a little early, you can maybe guess that Dr. Vianna was actually at Mizzou at one point. So I just want to let you know that We'll take most questions via the chat box, and then we'll have two graduate students, Neil and Dane, will be monitoring the chat during the question and answer. If you'd like to ask Dr. Vianna your question directly, just raise your hand, and Neil and Dane will be watching and can call on you, just so we're not talking over each other. But with that, I'll let Dr. Padilla introduce Dr. Vianna.
All right. Good afternoon, everyone, and welcome to our NEP Zoom seminar. My name is Jaume Padilla, and I'm a faculty member in nutrition and exercise physiology. And today it's my privilege to introduce a very good friend and colleague, Dr. Lauro Vianna, who is virtually visiting us from the University of Brasilia in Brazil. Dr. Vianna obtained his PhD from Gama Philo University in Rio de Janeiro. And after graduation, he traveled to the University of Birmingham in the UK to work with Dr. James Fisher as a research associate. In 2010, he joined us here at NU as a postdoctoral fellow in Dr. Fidel's laboratory. And that is where we had the opportunity to not only work together as a postdoc fellows, but also to build a very nice friendship. In 2012, he went back to Brazil for another postdoc at the Fluminense Federal University, also in Rio de Janeiro. And 2 years later, he was offered an assistant professor position at the University of Brasilia, where he currently directs the Neurovascular and Integrative Physiology Laboratory. His research is focused on neurocontrol mechanisms of the cardiovascular system at rest as well as during exercise in both healthy human subjects as well as in patients with various pathophysiological conditions, including hypertension, heart failure, or Parkinson. He has been extremely prolific with a publication record of 86 peer-reviewed articles to date. He has mentored a number of PhD students and postdoctoral fellows during his tenure as an assistant professor, as well as he has received multiple awards from the American Physiological Society, which recognize his excellence in research. Indeed, Dr. Vianna is an outstanding mid-career scientist. Today, we will learn about his work related to the exercise pressor reflex, which is a topic that he has been studying for a number of years. Dr. Vianna, the floor is yours, my friend.
Okay, can you hear me? Well?
Yes.
Well, thank you, Jaume. Thank you, Jackie. Thank you, NEP, for the invitation to be here and talking to you about some of our work. For me, it's a really, really honor. I was telling Jackie that I have a lot of affective memories about being in Mizzou, and I miss all my friends. I miss the university. University of Missouri, Columbia is a really good place to be. And I was really fortunate to spend almost 2 years over there. And being back today is a really great honor for me, and I'm very happy for this opportunity. So thank you again, Jaume. You are a great friend, and you are a really good inspiration for me. And I thank you for the introduction. So today we're gonna be talking about exercise pressor reflex, and I got myself inspired by Buzz Lightyear when I decided to say a journey to the brain and beyond. So I tried to make a little joke about this, but that's what we've been doing for the last 5-7 years at the Neurovasc, our lab here at the University of Brasilia. My lab and my work has been based on this statement here. So the proper function of feedback mechanisms is essential for an organism to respond to the homeostatic challenge associated with acute exercise stress. And that is related to the work by Walter Cannon that stated that the ability to respond to stress is related to health and longevity. So I'm quite interested to understand the underlying mechanisms as well as integrative responses and control mechanisms. How the human body respond to stress, as well as how several kinds of disease states or clinical condition, or whether you are male or female, that may be affecting the ability to respond to an acute stress. Can be mental stress, physical stress, or mental stress. And to begin with, we're going to go back to 1913, where August Krog and Johannes Linhart first reported an immediate response, heart hit response, at the onset of exercise. You can see here in the y-axis, you can see heart rate response. Here you see the heart rate, and here rest condition and 10, 30, 40 seconds of exercise. As you can see, the first beat after muscle contraction, you have a rapid increase in heart rate. And the magnitude of increase in heart rate is dependent on the intensity. So you can see here, 30 kilograms meter, 700, 2200. So as you increase the intensity, the magnitude of the response are similarly augmented. So that was shown in 1913. After 100 years of study in this area, several mechanisms have been postulated and suggested in the literature as being important mechanisms that might be mediating or contributing to changes in parasympathetic activity to the heart, sympathetic activity to the heart, sympathetic activity to the vessels, and adrenal medulla that releases neurotransmitters in these end organs that at the end it's going to promote changes in cardiac output and vascular resistance, change in pressure, the output of these hemodynamic changes. And the mechanisms are, the major mechanisms are central command, carotid chemoreflex, arterial baroreceptors, and cardiopulmonary baroreceptors, as well as respiratory metaboreflex. Although we recognize their role in mediating autonomic changes to the heart and to the vasculature, today we're going to be focusing on the role of exercise pressure reflex in mediating the responses in the vasculature as well as in the human heart. So in terms of exercise pressure reflex, this is a neurofeedback comprised of two arms. One of the arms is called metaboreflex, and the other one is called mechanoreflex. As the name is very suggestive, the metaboreflex arm are basically metabolic sensitive receptors that are sensitive to the metabolism, the metabolic changes within the contracting muscle. On the other hand, mechanoreflex are sensitives, are mainly mechanically sensitive receptors that predominantly senses the changes according to intramuscular pressure or mechanical distortion during muscle contraction. Those receptors generates information to the brainstem. That information is processed in these cardiovascular areas within the brainstem, and then generates an output that is vagal withdrawal and sympathetic activation that's gonna ultimately change blood pressure, heart rate, and left ventricular contractility. In terms of its neurophysiological basis, we have this table here that you may know some of these properties of these sensory nerves within the skeletal muscle. Those are the major ones that we have in textbooks. But today we're going to be talking about the group 3 afferent fibers and the group 4 afferent fibers. So the group 3 afferent fibers, they have this velocity of conductance, 2.5, 30 meters per second, and they have nerve-free ending fibers. The group 4 fibers, they don't have myelinization, and they have consequently, they have low conductance velocity. And they are also nerve-free end fibers. So in terms of topographic localization within the skeletal muscle, group 4 fibers, they are located close to blood vessels, as you can see here, whereas group 3 afferent fibers are more closer to the skeletal muscles or myotendinous junctions. So it is interesting to raise the question whether there is an anatomical functional coupling. So whereas the group 3 fibers are near to the skeletal muscle fibers, the muscle myotendinous junctions, the group 4 fibers are located near to the blood vessels. So in terms of how we can test the mechanical reflex or the exercise pressure reflex, more specifically the muscle mechanical reflex in humans. So this model was proposed by Araújo and Nóbrega, whereas we have a tandem bike where the back guy here pedals, whereas the front guy stay quiet while their legs are passively moved. So they are instructed not to move while this guy here is actually pedaling the bike. You can see the trunks here are swept in order to, when this guy here are pedaling, this leg here is being moved passively. What we can see is that in the black circles here, we have the heart rate response to active cycling, and the white circles, we have the passive cycling. You can appreciate in the first 4 seconds, we have a significant rise in heart rate, and this rise was similar between conditions. It's important to note that during the passive cycling, we don't have voluntary movement. So we don't have central command. We don't have brain structures inducing those heart rate changes. That was the first piece of evidence indicating that the muscle mechanical reflex are really important in mediating increases in heart rate during exercise in humans. So this model is quite interesting, was developed here in Brazil, and we're gonna be showing some data performed in our lab using this model. The muscle mechanical reflex can be tested by using a technique that is called post-exercise ischemia that was first shown in 1937. Here we have systolic blood pressure. In red, we have exercise. You can see a nice increase in blood pressure followed by a drop in pressure during recovery time. When this exercise is performed under cuff ischemia, you can see here, the rise of blood pressure is quite prominent, is quite greater, it's augmented. And when the person is, the individual is oriented to stop exercising, but pressure stays high. That means the techniques that is being used, the cuff ischemia, that can trap the metabolites that is being produced by muscle contraction within the muscle, and those metabolites cannot come out. So they stay there, depolarizing those neurons sensitive to metabolites within the muscle that was contracted during exercise. And that was enough to maintain blood pressure elevated while there's no exercise being performed. So that was the first evidence suggesting that we have sometimes of neurons within the skeletal muscle that are able to provoke a significant increase in blood pressure. Another model we used, we're going to be showing some data for you. It's a model that we can, at the level of the spinal cord, between the L3 and L4, we can infuse a kind of opioid agonist of mu receptor that can block or at least impair the afferent information coming from the periphery, from the contracting muscle. So at the spinal cord level, we can impair the communication being made between the neurons at the spinal cord level. When you infuse intrathecal fentanyl here, fentanyl is going to compete for the same receptor as being the neurotransmitter that is being released from the muscle contraction. So when you infuse opioid there, that is going to basically compete for the same site that is going to be made the transmission from the exercise. So what we can see is that you are doing exercise, but the brain is not receiving afferent information coming from the contracting muscle. So what we did in order to show you and convince you how those muscle afferences are important to cardiovascular homeostasis in humans, we performed these studies. We had this 8 healthy, active men, 28 years of old. We had them exercising at a very low workload. We have blood pressure being measured directly within into the brachial artery. We had respiratory band on. We have several things going on. And after they exercise for a 5 minutes bout, we put them on the medical bed. We infuse fentanyl, and then we put them back on the bike and see how the infusion of intrathecal fentanyl could be affecting cardiovascular responses to exercise in humans. Those studies were a part of PhD thesis led by Thales Barbosa that is currently located at the University of Mississippi. What we can show you about this set of data is that at the very onset of exercise, we have a nice increase in blood pressure that is followed by a drop below baselines. And then after 10 seconds, this rise in pressure is consistently progressively happening. In the face of fentanyl, when we put fentanyl, we don't see the third phase of the rise in pressure. Pressure stays down. So the fentanyl, intrathecal fentanyl, impairs the neurotransmission at the spinal cord level of the muscle afferent information coming from the muscle contraction. So we can highlight here the role of those muscle afferences in cardiovascular homeostasis during exercise in humans. So as an outline for you, we have two stories today. I'm going to talk about some peripheral and central neurotransmission that is divided into two stories called 1A and 1B. And the second part of my talk, I'm going to be highlighting the exercise pressure reflex in two different kinds of disease. And intentionally, I work with hypertension here and Parkinson disease, that I'm going to show you how these diseases can affect completely in the opposite way exercise pressure reflex. So I'm going to highlight exercise pressure reflex in disease, hypertension, and Parkinson disease. So to begin with, those are the responses where we use in our model, the post-exercise ischemia model. We call isolated muscle metabolic reflex activation during post-exercise ischemia. So we have a nice increase in pressure, and during post-exercise ischemia, we have a sustained increase in pressure. Heart rate tends to come down to baseline, and sympathetic nerve activity here in this panel, integrated muscle. Every single spike you are seeing here is a sympathetic discharge. There is an amount of neurotransmitter being released in the synaptic cleft. That means that the muscle cells are going to be contracting and increasing vascular resistance. So the greater the sympathetic activation, as you can see here, the greater the rise in pressure, usually. Not necessarily always, but it is commonly observed this way. So you can see the first minute of hand grip, static hand grip exercise, second minute, and here we have the isolated muscle metabolic reflex. So this is a pretty standard response we can see in the lab. However, despite this knowledge, the receptors activating the group 4 fibers that are important to mediate the exercise pressure reflex function are largely unknown. There is one paper, classic paper led by Professor Scott Smith from University of South Medical Center in Texas. They show that TRPV1 receptor is an important mediator of the exercise pressure reflex in rats. And they got a bunch of Sprague Dawley rats. They did a hind limb muscle contraction, passive muscle stretch. So hind limb contraction, trying to elude about metabolic reflex, and passive stretch, trying to activate mechanical reflex. And what they got is this. So here in the y-axis, we have mean arterial pressure. We have pre-treatment. We have when we contract the muscle, they contract the muscle, we have a nice increase in blood pressure. And then when they infuse capsaicin capsaicin was injected into the hind limb arterial supply, which is an antagonist of TRPV1 receptor, we have a really nice blunting of the pressure response to contraction 1, contraction 2, 3, and 4, as you can see here. When they did muscle stretch, they didn't see any effect of the blocking of TRPV1 blocking. That means that TRPV1 receptor might be contributing to exercise pressure reflex through the metabolic reflex arm, not through the mechanical reflex arm. So the question we made is whether we could extrapolate these animal findings to human. So we decided to get 8 healthy male subjects, 23 years old. They performed hand grip at 40% maximum voluntary contraction, followed by post-exercise ischemia, and they performed this exercise 40% before and 30 and 60 minutes after application of a commercially available capsaicin balm. So this is our setup. We have finger arterial pressure, beat-to-beat blood pressure, pneumo trace, cuff in order to isolate metabolic reflex following exercise. We have in the volar part of the forearm capsaicin balm on, and also we measure femoral blood flow. And here we have a very challenging technique where we place the tungsten electrode, microelectrode, in order to directly measure postganglionic sympathetic discharge in humans. This is our data. We have spikes here. That means sympathetic activity, and here sympathetic activity during isolated metabolic reflex activation. And then after capsaicin balm, we have nothing happening during baseline, and we observed a really nice decrease in sympathetic discharge during post-exercise ischemia. As a group value, we have in the white bars, we have experimental set, and the black bars, we have a control session. T0 means pre-capsaicin, T30, 30 minutes after capsaicin balm application, 60 minutes after capsaicin balm application. As you can see, 30 minutes after, we have a nice decrease in sympathetic responses to metabolic reflex activation, while in the control condition, we don't see a decrease. The same happened in a different magnitude to blood pressure. We have a nice augmentation blood pressure pre-capsaicin, and this increase was attenuated 30 minutes and 60 minutes after capsaicin balm application. So as a first summary, we have that transient receptor potential vanilloid 1 contributes to the exercise pressure reflex via its metabolic component in humans. The second part of my first story is how those information, electrical information from those neurons are being transmitted into the medullary cardiovascular areas. In order to do that, we understand that we have several chemical synapses within the central nervous system. And we know that from animal studies that synapses related to GABA, NO, for example, are important mediators of the exercise pressure reflex. But we decided first to highlight and focus on the GABAergic neurotransmission because of a few papers that I'm going to highlight in the next slide. The GABAergic connections, we have basically, in terms of GABAergic connections, we have 3 different subtypes of receptors. They are GABA A subtype, GABA B, and GABA C. we're going to be talking about the GABA-A receptor that are dependent on chloride conductance within the receptor, within the neuron, that's going to make an inhibitory effect into the neuron and the nuclei that is being connected. Why we decided to target GABA-A receptor, that was inspired by Jeffrey Potts, published in Neuroscience 2003. What they showed was, I'd like you to focus on the baroreceptor control. We have here in this panel contraction of the muscle, pulse pressure, heart rate, and here kind of baroreflex index. So the bigger the bar here, the bigger is the presence of baroreflex control. So in this experiment, we have a nice increase in pressure that provokes reflex bradycardia here. We have a drop in bradycardia. So this relationship between rising pressure and the reflex bradycardia, we can see here the representation, this bar here. When we have this condition concomitantly with muscle contraction, as you can see here, we don't see bradycardia manifestation. As you can see here, the lack of bradycardia. That means that baroreceptor is being inhibited by muscle contraction, by afferences, inflammation coming from the muscle contraction. What Jeffrey Potts did was they did bilateral infusion of bicuculline, that is an antagonist of GABA-A receptors within the NTS. And what they showed, when the GABA-A receptor is being blocked, it is quite important that they were able to restore the bradycardic response to the rise in pressure, although we are having here muscle contraction. That means that was the first piece of evidence that GABA-A receptors are important central mediators of the exercise pressure reflex. So our hypothetical model is that at rest, parasympathetic activity is under tonic control of cardiac motor neurons, as you can see here. And also sympathetic outflow or premotor sympathetic neurons are under inhibitory control of CVLM, caudo-ventrolateral medulla, that has a tonic and inhibitory effect on the RVLM, right? Where we have the projections of premotor sympathetic neurons. That's gonna make connections to the vasculature and to the heart. When we have exercise on the top of that, we inhibit the control, bit-to-bit control of arterial bar reflex information going into the NTS. And then the inhibitory effect via GABA-A receptors are augmented here through the information coming from the EPR, the exercise pressure reflex. And that allows an increase of an inhibitory effect of the tonic information into the RVLM, and allows an increase in sympathetic activation to the vessels and to the heart. The end of this, it increases, as I said, cardiac output, vascular resistance, and blood pressure. We decided to postulate this question here, and this study was led by Dr. Teixeira. He is currently a postdoctoral fellow at the University of Guelph in Canada. So we decided to ask whether GABAergic mechanisms are involved in the neurocardiovascular responses to exercise pressure reflex activation in humans. So GABA-A receptor, we can play with that in humans by using a benzodiazepine that is called a positive allostatic modulator of GABA-A receptor. So the binding of benzodiazepines promotes binding of GABA. GABA is being released from the context of muscle afferences into the NTS, which in turn increases total chloride conductance and then inhibits these neurons to a greater degree. Thus, the action of benzodiazepine or benzodiazepines, is considered to be a cooperative enhancement of the effect of GABA, and has been used to investigate the role of GABA at the GABA-A receptor level in humans. So we decided to pursue this approach by using Valium or diazepam. It's a drug that many people use for different reasons, muscle relaxation, or even depression and other schizophrenia and other psychiatric conditions. And we decided to use the passive model. As we showed before, we involved 28 subjects, 14 women, 14 men. We also used EMG in order to guarantee the subjects were not voluntarily helping the movement while they were being passively moved. And what we showed is the heart rate increase quite similar to what Dr. Nobrega and Araujo showed in 1993. And when we gave diazepam to our subjects, the augmentation heart rate at the onset of exercise was augmented. And this was not different in terms of blood pressure in between men and women. The second study, we decided to look at the sympathetic branch. So the heart rate at the onset is mainly dependent on the vagal withdrawal. Now we decided to look at how sympathetic is being affected by GABA-A, whether sympathetic outflow to exercise is being regulated or controlled by GABA-A receptor. So we had this setup. We did a randomized double-blind placebo-controlled crossover design. 17 healthy subjects was involved. They did a ischemic isometric hand grip exercise at 30% maximal voluntary contraction. This is our setup. Again, we are using microneurography technique in order to measure sympathetic discharge. This is our responses: blood pressure, heart rate, and muscle sympathetic nerve activity during baseline, exercise, and metabolic reflex. This is all before GABA-A receptor activation. And here we have a after condition, 1 hour after diazepam administration. I would like to call your attention the amount of spikes we have before and the amount of spikes we have after diazepam. You can clearly see an augmentation sympathetic discharge after diazepam administration. And here's the summary results. We have response to exercise augmented, as well as during metabolic reflex activation. Here we have a placebo control condition. We don't have those changes. We were able to recapitulate what we showed in the first set of data about heart rate. We also got during isometric exercise an augmentation in heart rate after diazepam, and we don't have anything happening during control condition. Blood pressure was also augmented, you can see here, during exercise as well as during metabolic reflex activation. So, a summary, the first part of the story is GABA-A receptors significantly contribute to the muscle mechano-reflex-mediated heart rate responses at the onset of exercise in humans. And GABA-A receptors are involved in the regulation of sympathetic vasomotor outflow and the pressure responses to muscle metabolic reflex activation in humans. We decided, Andrea was really, several times I provoked Andrea. Andrea is an outstanding scientist, and he decided to propose a pedagogical way to make the post-exercise ischemia maneuver more accessible to undergraduate students. So I would like to invite you to take a look in this paper. I'm not gonna talk today about this, but I would like to share with you that was an extremely valid experience proposing this method. The perception of our students was greatly improved after exposing them how to, and showing the post-exercise ischemia maneuver in order to provide them a better comprehensive understanding of how exercise provokes cardiovascular responses in humans. The second and the last part of our stories pertains to the exercise pressure reflex in disease in terms of the hypertension and Parkinson disease. And the reason why I decided to talk about these two diseases is that related to the fact that hypertension affects in a completely opposite way the exercise pressure reflex when compared to the Parkinson disease condition. So to begin with, I would like to show that hypertensive patients are not only hypertensive at the medical office. When you ask them to squeeze or just carry a bag of a grocery store or just go upstairs or go downstairs, their blood pressure is going to be further elevated. So we have an example here in this paper, 30 seconds of exercise. We have a nice little increase here in normotensive subject, and this was greatly augmented in hypertensive subjects. As you can see, the augmentation and the pressure response in this kind of patient, it doesn't take too long to be manifested during exercise. The first few seconds, only 10 seconds, you can already see that there is an augmentation in the pressure response to a small muscle mass exercise. The problem is that those patients, they have other problems that in face of an augmented pressure response, that may provide a really bad environment for the system to operate. And I would like to highlight a study that I conducted here over there in Missouri. So every bar here, we have the quantification, how the brain is buffering the changes in blood pressure in control subject. So you can see here, baseline, you have a nice control of the brain circulation. Under moderate intensity exercise, the autoregulation is preserved. And during 40% high intensity hand grip exercise, it is also preserved. When we get hypertensive subjects, as well as hypertensive subjects or with type 2 diabetes, actually type 2 diabetes and type 2 diabetes with hypertension, you can see that they are already coming out from a lower autoregulation index, or that means they have a blunted ability to buffer changes, abrupt changes in blood pressure at rest. But when you put them under exercise condition, their ability is further decreased. So you get this together. So the brain of a hypertensive subject is not working the way that it should be. And in the face of that, their blood pressure is being augmented. It's greatly augmented during exercise. So this is a perfect environment to provoke vascular injuries and perhaps a stroke in the long term. So we decided to ask the question whether fentanyl, intrathecal fentanyl, could normalize the exaggerated elevation in blood pressure in hypertensive men during cycling exercise. So this is our illustration here. Again, we have the subjects exercising. We have arterial brachial artery catheterized. We measure blood pressure directly into the artery. They were non-treated, never treated hypertensive subjects, very hard to find them. They were asked to cycle, to do a cycling for 5 minutes at 40 watts, intentionally 40 watts of extremely low intensity exercise. And that was in purpose because we would like to show that even very low workload exercise, their blood pressure is already augmented. After cycling for 5 minutes, lumbar intrathecal fentanyl injection was administered, and then we repeat cycling for 5 minutes at 40 watts. So this is the response we got from a normotensive group of subjects. We have a nice and small increase, but consistent increase in blood pressure. And that was accompanied by a augmented, greater increase in blood pressure in hypertensive subjects. When we do administered intrathecal fentanyl, we have a really nice normalization of their exaggerated blood pressure response. So exercise pressure reflex is an important mediator of the exercise pressure response to exercise in human hypertension. The other question is related to Parkinson's disease, which is the second most common neurodegenerative disorder in humans. And it is greatly known by its motor impairments, mainly the tremor that we all can see when we see we can observe when we see a Parkinson's disease patient, a patient with Parkinson's disease. But in our lab, we are mainly interested in the non-motor features of these patients, mainly those that might be affecting their quality of life. One of them is the blood pressure control during exercise. So in 1987, in the Journal of Neurology, it was shown that these patients, they showed a decreased attenuated pressure response to exercise, both systolic and diastolic. We decided to ask whether metabolic reflex as an important arm of the exercise pressure reflex. We decided to ask whether this could be an important underlying mechanism that might be contributing to these blunted responses. So we have here Jean Sabino Carvalho, is my PhD student. We've been working together for the last almost 4 years. And I'm very happy to share with you some of our data that came out at the Journal of Neurophysiology in 2018. So this is our experimental setup. We have the subjects, the patients seated. We have EKG on, a cuff occlusion in order to isolate metabolic reflex in the forearm, respiratory belt, hand grip, finger photoplethysmography. Very standard setup. So we can appreciate here in the panel A, mean arterial pressure in the y-axis and the x-axis time in seconds. We have in CT, we have a control patient, control subjects, have a nice increase in pressure that is maintained during post-exercise ischemia. In Parkinson's disease patient, they manifest an increase in pressure, and that was further attenuated during metabolic reflex activation. So focusing now on the panel D here on the right, you can see that during post-exercise ischemia, the responses, blood pressure responses are further attenuated in PD patients. But one question that Jean decided to make is this in a specific blunting related to neurons, exercise neurons, or let's say it could be a generalized neurodegenerative effect that might be affecting the central nervous system processing of the peripheral information. So we decided to raise their pressure using a really hard test that is called cold pressure test. So they put their hands into the ice bucket here, and then we have the control subjects having this kind of response, and then the Parkinson's disease respond in a similar manner compared to their counterparts control. So exercise pressure reflex is an important mediator of the blunted pressure response to exercise in patients with Parkinson's disease. And we may speculate that this might be a specific physiopathological problem or underlying mechanism of the disease, because their ability to respond to cold pressure stimuli is preserved when compared to their controls. So today, in summary, I think I was able to convince you that the exercise pressure reflex starts somewhere here in one of those receptors, in particular the TRPV1 receptor. It also is important the connections at the spinal cord level, as we showed with some intrathecal fentanyl studies, and they possibly might be contacting and make contacts to the brainstem via the release of GABAergic connections and making connections through the GABA-A receptors. And I invite you all to take a close look in our paper that was featured in the cover of Exercise Sport Science Reviews in the April issue. that I have a privilege to co-author this, invite to review with André Teixeira, Igor Fernandez, a great friend to me, and André Teixeira, that I had a pleasure to be his PhD supervisor. To my acknowledgements by all these people, Dr. Igor Fernandez, Jean, Fernanda, Camila, Thais, Fabrício, Rafael, and Gustavo Lopes, and also all my collaborators, especially to André Teixeira, Thales Barbosa, that made this series of studies, invasive studies, possible, and was really motivated for me to work with these two colleagues. Thank you.
Nice job. Thank you.
Yeah.
Thanks, Dr. Vianna. Very nice presentation. I'll have to check this recent review article, and definitely I'm not surprised you made it the cover page. It's a beautiful, beautiful illustration that you came up with. Did you draw this?
No, actually, we had a professional person doing that for us. But this illustration was basically, we brainstormed that illustration, but Igor Fernandez, he led basically the whole job about making that illustration possible. So he should take the credit.
Very nice job. I think we have a few minutes now if people have questions. I'll make sure I'm following the correct instructions, Dr. Lindberg. Is that appropriate for people to unmute and ask questions directly? We have 2 graduate students here monitoring. So I think I'll let them.
If they raise their hand, if Neil and Jane can just call on them so that not everybody talks at the same time, or type it in the chat, that'd be perfect.
Okay, if while people start thinking about questions, I'm gonna ask the first one. As you were presenting, one thing came to my mind is, do you envision that the next step from a translational standpoint would be to identify novel therapeutics to treat the exercise pressor reflex in hypertension, and that perhaps those therapeutics will be different than medications typically used to treat hypertension? Is that what you envision to be the next step from a therapeutic and treatment standpoint?
Yeah, very good question, Jaume. Yeah, I think I'm trying to go in 2 different steps. I'm trying to target the central nervous system directly, and also I'm trying to target the skeletal muscle. I know Marcus Amann at Utah, he's doing some kind of cocktail in order to attenuate the oxidative stress and make the receptors less expressed in those neurons, aiming to attenuate the amount of pressure response to exercise. I'm targeting the receptor itself using capsaicin balm chronically and see how this could be possible. The problem is that the capsaicin balm is an agonist, right? But the receptor, in the presence of its agonist, became desensitized, right? So it doesn't respond. The problem is that the capsaicin balm, it targets the muscle, it goes into the muscle, but it is not that specific to the TRPV1 receptor. It can destroy other receptors. So I don't know whether that effect I'm seeing, that setup, that is really due to the TRPV1, or it's been a generalized effect of the capsaicin balm. Another way I'm trying to target the exercise pressure reflex is trying to change the metabolites within the brainstem by using electrical stimulation, transcutaneous electrical stimulation in the tragus. So we have some papers published in the Brain Stimulation, a high impact fact journal, showing that acutely I was able to tackle bioreflex sensitivity. I was able to increase bioreflex sensitivity, which is an indication that I was able to manipulate autonomic nervous system by using transcutaneous stimulation. So I'm trying to use neuroimaging studies in order to show this possibility, showing the environment into the brainstem and see how those electrical stimulation, external stimulation, could be promoting a better central integration environment that's going to be making the context, right, from these afferent nerves. So those are my pathways: central nervous system and targeting receptors itself.
Very exciting. Yeah, thanks for sharing those thoughts and ideas.
Yeah.
Dr. Vianna, great talk. So I'm going to field the first question from Dr. Limberg, and it was, do patients with Parkinson's disease have a greater risk of falls or syncope, I assume from this altered autonomic phenotype?
Yeah, very good question. I mean, those patients, they are over 60, they are 65 years old, and 40% of those patients, they manifest orthostatic hypotension. And that affects tremendously their quality of life. They don't want to stand up. They don't want to come out of the chair, not because of the tremor itself, just because they're going to feel dizzy. They don't want to come out of the chair, the couch. So, those 3 of those patients manifested orthostatic hypotension. We tested all of them, but they didn't show pressure response different, dramatically different from the rest of the group. Of course, we need to further investigate that according to this clinical manifestation. But that's a good question. We would like to have more data on this in order to have an idea how these other non-motor features could be affecting the pressure responses to exercise.
Awesome, thank you.
All right, we have another one here. Do you think central dopamine dysregulation affects the processing of afferent feedback in the brainstem, perhaps contributing to the blunted response in Parkinson?
I don't have any idea about this. As I said, I mean, those afferences, as we know so far, are affecting the brainstem via GABAergic connections. We know some data from the substantia nigra. They have less GABAergic neurons, right? So I think that might be something there, but we have to look at our data. We asked them to put their hands in the ice bucket, right? So if this suggested mechanism were affecting, that would be also affecting the pressure response to cold pressure test. So why that would be just specific to the exercise pressure reflex? So right now, what I have with my hands is that I believe that the exercise pressure reflex is being affected, affected by the progression of the disease. It's an exercise mechanism that is being affected.
Thank you.
All right, so now we have another question that, and I think this is a great question from Talia. Has the exercise pressor reflex response been tested with other CNS-related diseases like multiple sclerosis or ALS or something like that?
Excellent question. I know that Scott Davis from Texas, they've performed some studies with neck suction activating feedback from the carotid bar reflex. And they also they were able to measure postganglionic sympathetic discharge under resting conditions, very challenging to do CNS patients. So they showed extremely low sympathetic firing at rest condition. They showed impaired bar reflex control of blood pressure and heart rate in those multiple sclerosis patients, but we don't know about exercise pressure reflex in those patients. We don't know yet, but it's quite an avenue to pursue. Quite important question.
Great, thank you. And I actually had a question as well. So these drugs that you've used, diazepam and fentanyl, I know that they have like dynamic receptor changes if used more than once. So do you think that the exercise pressor response would change, or the autonomic response to the exercise pressure would change if used more than once or acutely?
I've never used more than once. So, and also one thing that we might be, cautious about my experiments is that the intrathecal fentanyl is placed while the subject seated. And we did that in order to avoid cephalate migration of the drug to the central nervous system, right? And also we use hand grip exercise or a connection higher up at the spinal cord level, aiming to have a preserved the pressure response. So the blocked is being made lower at the spinal cord. So we have this set of data published as well, showing that there's no migration from a higher point at the spinal cord. In terms of GABA receptor, of course, we believe that might be affecting the central nervous system, but we have GABA receptors everywhere, especially in the spinal cord level as well in humans. So, but we believe, based on the literature, if there is a peripheral effect on our data, that is a bias against us. So if we could isolate the GABA receptor effect with diazepam in the central nervous system, I think the responses we are seeing here would be further augmented, I would say, just to give you an explanation about these drugs.
That was excellent. Thank you. But I don't see any other further questions in the chat, so I will turn it back over to Dr. Pia to thank you again.
All right. So if we don't have any more questions, I want to thank Dr. Vianna again for this very nice presentation and for sharing his current work in exercise pressor reflex. I think we all learned a significant amount of information today. It's great to see you again, Lauro. Please say hello to the family.
Yeah, I'll do. Thank you, Jaume. Thank you all the audience here. I'm very, hey, Jill, I see you.
Good to see you, Lauro.
Yeah, my pleasure. Miss you. Yeah, I said I have a really affective emotions about Mizzou. I love Mizzou. I love the people. I was really inspired about all these giant scientists that were there while I was during my postdoctoral fellowship. I was really fortunate to.
Well, we hope to have you back post-COVID. We're definitely gonna have to come,
Yeah,
for real.
Yeah, thank you.
We'll have
it would be a pleasure to come back and see you guys.
All right. Thank you very much. Thank you all for attending.
Thank you.
Very nice work. All right.
Thank you. Thank you, John. Thank you, Jackie.
Thank you so much. It was great. We really appreciate it.
Thank you.